Our next presentation is exploring the potential of smartphone GNSS and accelerometer observation for disaster monitor and will be made by Dr. Jacek Paziewski.
Okay, thank you very much for the introduction. So my name is Jacek Paziewski. I work at the University of Warmia and Mazur in Olsztyn, and in this presentation, I would like to respond to a question whether the smartphones, GNSS observations, and accelerometers can be used as the detectors of the dynamic displacements. Can we show the presentation somehow? Oh, okay, much better right now. Okay, let's move to the motivation. In case of dynamic displacements that can be seen in structural health monitoring or seismic studies, conventionally high-grade GNSS receiver are used. So this is quite reliable sensor, a detector of the displacements with the high-rate solution. However, there are also some limitations of such network builds of the high-grade receivers because sometimes the density of the sensors or of the receivers may be insufficient for a particular area. Now, with mass market GNSS receivers, we have the opportunity to densify the networks with low-cost receivers and also with the smartphones. Next, we are also observing the growing potential of the smartphones GNSS observations, and some studies show that quite, let's say, good results can be obtained in the positioning domain. And in this presentation, we would like to extend the studies and verify the research hypothesis that GNSS observations that are collected by the recent smartphones, together, however, with the accelerations also registered by the smartphone, can be used as the sensors, as the detectors of the dynamic displacements with precise solution with the, let's say, sub-centimeter level. So we are using the two-step methodology. Basically, the methodology is quite often used in the displacement detection with high-grade receivers. So we are combining the GNSS observations and the accelerations in the Kalman filter. So from one hand, the GNSS observations from the smartphones can be obtained from now on only with 1 Hz sampling rate. So the support from the accelerations is needed to provide a dynamic solution of high rate, and in this case, much more dense sampling rate of acceleration is used because it is close to 1 Hz. So in the first step, we are providing GNSS-only solution that is based on the GNSS observations from the smartphones. And in this case, we are not using any position-based method like RTK or PPP, but we are using the methods that are, let's say, close to the variometric approach, like a VADASE. So the first one is the method when we are differentiating the phase-only observations between epochs. And in this case, the displacements in particular directions are our parameters or unknowns. Also, the change in the receiver clock collection is an additional fourth parameter. So we are also using some developments to the method because we are also differentiating not only between epochs but also between satellites. So this is the second equation, normal observation equation below. So in this case, the receiver clock changes between epochs is eliminated. So we have only 3 parameters. But well, the drawback is that we are a little bit we have a little bit higher noise of such kind of observation that it used in the estimation. So with such obtained GNSS displacements or coordinate displacements, are integrated with the accelerations that can be also recorded by the same smartphone. And in this case, 100 Hertz accelerometers are recorded. And this is done, as I previously said, in the Kalman filter. Final step is the backward filtering, because this is a post-processing solution, and we are using the Rauchtung-Striebel smoother that can enhance the solution from the previous epochs. So such methodology was employed in the and verified in the experiment that is based on the simulated vibrations or displacements, and we are using a shake table to simulate a single axis displacements of different amplitudes and different frequencies. So in this case, we have simulated 6 sine wave motions of the frequencies of 0.1 or 0.5 Hertz. And from my point of view, the most important is the amplitude, because we are using the amplitude. The maximal was 20 millimeters, and we are going down to even 5 millimeters and try to detect such vibrations. We are also simulating 2 seismic earthquake waveforms, El Centro, El Cape Mendoncito, if I pronounce it correctly. So the peak ground displacement in this case was 18 millimeters. So these are our, let's say, benchmark displacements, because the shake table can register its position, so the displacement, quite precisely. As the sensors to collect the GNSS and accelerometer observations, so we are using the Xiaomi 13T smartphone, so it's quite a new one. So this is our, let's say, main sensor for collecting GNSS and accelerometer observations. We have also collected GNSS observations with the benchmark receiver Trimble alloy that is combined with the SEM10 antenna, and in this case 20 Hertz GNSS observations could be collected, but this is only to, let's say, to provide a benchmark result for GNSS solutions, not the ground truth displacements. The GNSS and accelerometer observations from the smartphone was collected with the Google GNSS logger, so the Rhinex files and the text file with the accelerations was recorded, and we are processing the observations in our in-house developed software, where the methodology that I mentioned previously was implemented. So first, we focus on the GNSS-only solution. So in this slide, you can see the retrieved displacements from the smartphone GNSS-only solution and the displacements from the Trimble alloy. On the left-hand side, in the first and third panel from the top, you can see the retrieved displacements. In the second and in the bottom panel, you can see the residuals, the displacements residual that were obtained as a difference to the ground truth displacements. And basically, here we have results for the, let's say, less challenging motion of the amplitude of 20 millimeters. We can see that both smartphone and, of course, Trimble receiver can detect the displacements quite precisely, let's say. So they follow the pattern of the sine wave. On the right-hand side, you can see the histograms of the displacement residuals as compared to the ground truth displacements, and the comparison between 2 methods that were used to process GNSS-only observations. So between epoch differencing and between epoch and between satellites differencing. So there are, of course, slight differences between the two methods, but I will go back with more precise results later. If we take a look of more challenging motion of 10 millimeter amplitude, we can see that again we can, let's say, provide or capture the displacement with the smartphone observations. There are, of course, some differences, and the standard deviation is more or less about 4 or 6 millimeters, depending on the method that were used. But basically, we can try to detect provide the displacements. When it comes to the most challenging motion of 5 millimeters only, basically GNSS observations that were recorded by the smartphone failed to recover the scene wave motions that were simulated. So basically, with the smallest amplitude motions of the smallest displacements, so smartphone observations are not, let's say, good enough to provide a solution. Of course, in the method that were summarized by me. So, as our goal was to provide a millimeter level solution or close to the millimeter, in the next step, we are combining the GNSS observation, GNSS displacements with the accelerations in the Kalman filter. And such results can be basically seen here. On the left-hand side, you can see the scene wave that were derived from the combined solution, where GNSS and accelerometers are used, and such results are given in the red. In the green, you can see the benchmark or ground truth displacement that were simulated in the shake table experiment. So we can see that the accuracy improvement is very good, and providing the root mean square errors that were computed as the difference between our solution, our combined solution, and the shake table position, we can see that the, let's say, precision of about 3 millimeters can be provided with smartphone GNSS observations. Also, if we take a look at right-hand side results, that the displacements during the simulated earthquakes are seen, we can see that the about 2.5 millimeter root mean square error is provided with the solution with GNSS smartphone observations and accelerations. So these results are also supported with the power spectral density, when we can see the combined solution in the red line and the GNSS only solution in the blue line. So these are the results of the smartphone only, and we can clearly detect the drop in the noise of the solution. Of course, the GNSS with the smartphone only observations are of different sampling rate because only 1 Hz solution is provided, but the combined solution GNSS and accelerometer is 100 Hz, as the Kalman filter was used for the final solution provider. To sum up, basically, if we aim to use GNSS only observations from the smartphone, we can expect the standard deviation or root mean square error of about 5 and 10 millimeters. So such displacement with such noise can be provided. If we focus on the method that can be used for providing GNSS only displacements between time differencing and time and satellite differencing, so they basically perform quite similar for the geodetic grade receiver. There were, however, slightly higher differences when it comes to the smartphone observations. But the most important lesson from the presentation is that smartphone GNSS observations and the accelerometer in the combined solution can provide the dynamic displacements with the root mean square errors of about, let's say, 3 millimeters. This is also holds true for the earthquake related displacements. So I believe that with that presentation we are quite closer to the using the smartphone as, let's say, fast detectors of some such dynamic displacements. However, there are still some practical issues that prevent us to, let's say, use it all the day. Okay. Thank you very much. That concludes my presentation.